Alright, what I'm going to do is I'm going to go over the third law worksheet, which has a lot of questions where if we're given the answers to them, probably couldn't be done so in just a quick number or something like that. A lot of times a good explanation to go along with it is actually better to see. So if I'm looking at the first question, it poses to a scenario where you got a car, small car, and a big truck. And the big truck is going to crash head on into the car. Now the reality is that we all know who the winner is in this collision here. When they crash, there's no question that the truck is going to annihilate the car, and the car is going to be receiving the worst of this collision here. But when we speak about the forces that are applied during that collision, that force of impact is simply a truck exerting a force on a car, and the car simultaneously exerting a force on the truck. It's not as if the truck gets out of this unscathed. So when they do apply forces to each other, you're going to have a force of truck on car, I'll call it T on C, and you'll have a force of the car on the truck. And this is an action-reaction pair. So what's going to happen is that they experience equal forces, but the truck annihilates the car because the car receives so much more damage because it has so much less mass. So the forces are equal, but the results aren't because they have different masses. That was number one. If you look at number two, you see like a farmer firing a rifle. So you got the guy, the rifle's in his hand, and what he's doing is he's firing a bullet, right? So in order to fire the bullet, the rifle has to fire the bullet. Now, let's not even think about the hunter. Let's think about the gun and the bullet here. If we're looking at those two things, what we want to recognize is that there was a force of the gun on the bullet, I'll call it G on B. And then what ends up happening is that if the gun pushes the bullet to the left, the bullet has to push the gun to the right. So I'll call this B on G to the right. And they experience equal forces as well. Again, you don't see equal results. The bullet clearly travels a lot faster than the gun, but the gun does move back. What it does is it's going to move back there. That's what we call recoil. Anything that fires something recoils, be it a Nerf gun, a cannon, anything at all that fires a projectile will recoil, and the amount of recoil depends upon what force was applied here. The next one is two people. We kind of already did that example. I think maybe we'll skip over that since I addressed that in another video. Their resulting accelerations would be different because of their masses. Number 4, you see someone dropping an object off the Leaning Tower of Pisa, but then when you see the ball falling down towards the earth, you have a force of gravity. We could call it the force of gravity, earth on ball. And then likewise, the ball exerts the same thing on the earth. Force of gravity, let's call that ball on earth. And these things are equal to each other as well. After that, we're looking at the moon and the earth. So if we're looking at these two things, this is actually a problem that we will tackle extensively in the next unit when we do circular motion. But for now, let's just look at the earth, which is here, and the moon, which revolves around it. Essentially, what you're going to find is that the moon orbits the earth, and it never quite escapes because there's a force of gravity acting on the moon that keeps it drawn in on some level. So we've got a force of gravity here. We'll call it earth on moon. Well, what the moon actually does is it causes the earth to wiggle as well, because the moon's always exerting a force of gravity on the earth. So we'll call force of gravity M on E, and then you get your action-reaction pair again. And this is responsible for a lot of things that occur on Earth, specifically, big waves and tides and things like that. But what you're seeing pretty quickly is that whenever one force exerts one on another, you get an action-reaction pair, and you get an equal and opposite reaction. Now the next one, I have an arrangement of 3 charges. So this applies to other forces as well. For example, an electrostatic force, which we really haven't learned about, but we do know that opposites attract and like charges repel. So if I look at that arrangement right there, I have these charges labeled A, B, and C. And so what I would find is that there's clearly going to be repulsion between these 2 positive charges. So I'm going to say that A pushes B away. Let's call this force of A on B. It's going to push it directly away from it. And then B is going to repel that as well. So we're going to call this FB on A. And this is an action-reaction pair right here. There will be attraction between these 2 charges because they are opposites. So I'm going to call this, there's going to be attractive force. C is going to try and draw in A this way. I'll call it force of C on A. A will also exert a force on C. These 2 things are an action-reaction pair. And the last one would be this one right here. We'll see attraction between these 2. So C would draw in A like that. And then likewise we would have a force here that we would call A on C. And those would be an action-reaction pair. So we have 2 forces acting on each object simultaneously in this particular arrangement here. Next up, magnets. Everybody loves magnets. Well, that was number 6, right? And this one looks like it's labeled number 6 as well. We're going to have to fix that. When you look at the arrangement of magnets, magnets can either attract or repel depending upon their arrangement. It is kind of like charges in that opposite poles attract. So you would see an action-reaction pair like that between these 2. But for the next 2 arrangements, you would see that, okay, well now we have the same pole facing each other. So that's going to result in repulsion. And so what you would get is one force acting on one and another force acting on another. Again, they would be equal. And the next scenario would also be repulsion because the new North Pole is facing. So I don't think I need to go through that one, but you would know that that occurs as well. All right, now this is labeled number 7. We've got iron here, just a block of iron, and we've got a magnet. So we know how poles interact because we've always, had some sort of magnetic toy that had a north and south pole. But you'd also see that, well, the magnets are attracted to the metal. So we would have the metal being drawn in by the magnet. We could call this the force of magnet on iron. But then the iron would also draw in the magnet. So we would call this the force of iron on the magnet. And that would be an action-reaction pair. So pretty easy scenario there. If you look at the 4 boxes, we're only asked to do A and B. So that's not a bad one. You've got A here, B right under it, and then there's the floor underneath that. So if we're looking at these forces here, you got A, B, and let's do the Earth, which is basically the floor here. It's force of gravity on A. Let's call it Earth on A. We use subscripts to keep track of things here. Force of gravity, let's call this Earth on B. And then A, I know, has a normal force acting on it. There's a normal force, and it's actually equal to the force of gravity here. So we'll call this normal force. It comes from the surface of B, so let's call it B on A. And then here's the thing about the normal force B on A. We know it's equal to this force of gravity vector right here. However, we gotta use the 3rd law here. If B pushes A up, A has to push B down. So there has to be a normal force downwards. Let's call that A on B. And it would be equal to that, which is also equal to the weight of A. So it's as if A is pushing down with a force equivalent to its weight on B. And what that does is that gives us another normal force, or a larger normal force, that's coming from this surface right here, from the surface of the Earth basically. Call it normal force Earth on B, and it's got to cancel out these 2 forces. So I would expect this force to be twice as large as the force of gravity. And then you're going to need an action-reaction pair, because if the Earth pushes B up, then B has to push the Earth down, so we'll call it normal force B on E. And then these two need action-reaction pairs, and you're going to find them pulling up on the Earth. FG, let's call this A on Earth, and then FGB on Earth. So you can see that I have accounted for all forces. Every force that's present has an action-reaction pair. Last question says that we have a car, and the car is sliding to a stop, and if we're trying to analyze action-reaction pairs here, there's quite a bit actually. This is actually a pretty complicated scenario, and it's not entirely obvious until you delve into the third law here. So here's your car. It's sliding to a stop. So, you know, there is friction causing it to come to a stop here. So what we want to do is we want to look at the forces acting on the car here. There's a force of gravity acting on the car. Let's call it FG. Comes from the Earth, E on car. The Earth is also pushing the car up. Let's call it the normal force, Earth on car. And then there's friction, right? There's kinetic friction, and it's got to be that way, FK. And let's say that that comes from the Earth as well, because it's coming from the ground. Earth on car. These are all coming from the Earth. So, if I want to say, well, what's going on with the Earth here? You know, there's your little car at the top of the Earth here. The Earth is getting an upward force of gravity from the car, so we'll call it car on Earth. It's got to be pushed down with a normal force car on Earth. And then this force here also needs an action-reaction pair. It's the Earth that's technically applying a force to the left on the car, causing it to slow down. Well, what the car is going to do is the car has to have that same force of friction pushing the Earth to the right simultaneously. So we'll call it force of kinetic friction car on Earth. And basically, we know that this force here is not really going to move the Earth because the Earth is so massive, but it is present. So every single force has its own action-reaction pair. That's the take-home message from the third law.